Hi guys, this is Samta Bajaj bringing to you in this video few smoke management techniques in the building fires. Fire is rightly called as a destroyer, and fire accidents are indeed a matter of serious concern in all kinds of buildings. Statistical data from Delhi Fire Office reveals that there have been around 27,343 fires in the year 2021-22. And in the previous year too, the figures were almost similar. And that left around 1421 people injured and caused around 591 deaths, which could have been avoided. So these are few recently reported fire incidents in Delhi. There was a massive fire in Metro Hospitals and Heart Institute, fire at Shahadra MS Park, fire in paper card factory of Archie's at Narayana Industrial Area, then at Bhavana Industrial Area, Delhi. So we see that all these fires have been so much disastrous. As per NFPA, which is National Fire Protection Association, a global self-funded non-profitable organization established in 1896 and is devoted to eliminating death, injury, property, and economic losses due to fire, electrical, and related hazards. As per NFPA, the total, the top fire causes in the fire incidents have been identified as those related to cooking, heating apparatus, smoking, and the electrical. But guys, whatever may be the cause of fire, the cost of fire accident is loss of life, damage to the property, loss of goodwill of the building because the building will earn bad reputation. And at the same time, it also causes environmental pollution. It's a well-known fact by now that smoke is a major killer in most of the fire situations. So, smoke extraction is an inevitable part of building design. So, what is so dangerous about smoke in building fires? Smoke kills, that is well known, but the reason why is much less understood. Data reveals that 75% of all fire deaths are caused by smoke inhalation and not the fire. Approximately 57% of the fire deaths have seen to be happening outside the room of fire origin. And you see, around 47% of the fire survivors, they reported that they could not see more than beyond 12 feet. Why? Because thick smoke reduces visibility, making escape of occupants very, very slow and hazardous. The typical speed of smoke is around between 1 and 2 meters per second, which is much faster than the escape speed of an occupant. So when the smoke reaches a dead end, whether vertically or horizontally, it will drop down or is drawn back towards the fire. This confuses the occupants and causes them to move towards the fire. So a properly designed and managed smoke control system is very important part of the building design. We all know that we cannot inhale smoke because of its noxious effects. We know it smells bad, and that's all about it. Fact is that in addition to being chemically toxic, hot smoke can be damaging to skin, eyes, and lungs and lead to disablement. It can obscure vision, hindering the escape of the occupants. This can further be understood by knowing the hazardous constituents of smoke. So you see, what is the composition of smoke? It contains the byproducts of combustion or incomplete pyrolysis, unburned hydrocarbons, and aldehydes. It's a mixture of liquid, solid particles and gaseous products, amongst which are all dangerous chemicals, molecules like carbon, hydrogen, sulfur, and nitrogen. Smoke can also be called as a mixture or a cocktail of carbon monoxide, carbon dioxide, HCl, and HCN, sulfur dioxide, and around additional 100 toxins. And smoke contains toxic and irritant gases, carbon monoxide and hydrogen cyanide being the most toxic of all. What are the other hazards of dangerous smoke? It is the generation of high temperature and the oxygen is reduced, oxygen levels are reduced, causes suffocation to the occupants. And you see, even the low concentration of carbon monoxide in an area, it can cause imbalance and diminished coordination and increased disorientation. It impairs visibility, can cause coughing, nausea, and vomiting. It causes irritation and respiratory problems, and it can inflict even death if it contains dangerous gases. So now, what are the applicable and regulatory codes for smoke control and management? The most prominent is IBC, the International Building Code. Then we have NFPA 101. NFPA 101, it gives the regulations for the new and existing buildings. Then we have NFPA 92A, which is the standard which defines the smoke control system through barriers or compartmentation and by maintaining the pressure differentials. The purpose of these is basically to keep the egress routes like stairwells, lift lobbies, and refuge areas to be free of smoke. And another purpose is prevent the travel of smoke from the smoke zone to the other adjacent areas. Likewise, there is another standard, NFPA 92B, which is a standard for smoke management system in walls, atria, and large spaces. The purpose of this standard is to maintain tenable environment in means of egress from the large volume building spaces. What is meant by tenable environment? Tenable means that where the conditions in terms of temperature and the concentration of contaminants are within the permissible limits and which are not life-threatening. And another purpose of the guidelines from NFPA 92B is to control and reduce the migration of the affected fire zone and prevent the smoke transfer between the fire area and the adjacent spaces. So if we compare with basically what is the difference between NFPA 92A and 92B, then the flow air patterns are opposite. While 92A seeks to move outside air into the enclosed spaces to keep them pressurized and free of smoke, and thus they have to provide exhaust relief also, because constant addition of air can cause excessive pressurization, causing problems in door openings. So exhaust relief is to be provided. And 92B, it seeks to move the smoke out of the large open spaces. So it takes care of the exhaust and provides intake relief to allow the smoke released freely. So basically, here they're talking of introducing makeup air, which will mix up with the contaminants, and the smoke can be then eliminated from the said space. Then we have the standard of NFPA 90A, which is a standard for installation of air conditioning and ventilation systems. Then ASHRAE applications, chapter 54, also addresses fire and smoke management. We have British standard BS 5588, which also defines smoke control in protected escape routes using pressurization. British standard BS 5720, it is a code of practice for mechanical, ventilation, and air conditioning in buildings. Then in India, we have NBC 2016, part 4 of which defines the fire and life safety. This standard was first published in 1970, and based on the experiences, because every fire incident is a experience, it teaches a new lesson. So the NBC 2016 has been revised over the years in 1983, 1997, 2005, 2015, and the latest one is NBC 2016. So guys, in any high-rise building, stairs are typically the main route for the egress of the occupants during a fire. So it is imperative for the exit stairs to be free of smoke so that occupants can escape safely. Now, how does the fire it travels in a building? What are the pathways of smoke in a building? These are the your stairwells. We have the lift shafts. It's also the structure between the wall and floor construction, because the wall and floor that is also permeable for the smoke to get transferred. Then we have the mechanical HVAC and the ventilation systems in place, and then the exhaust duct systems. So all these places, they provide the pathways for the smoke to travel. And what are the objectives of smoke extraction? The most important being the life safety, to reduce the damage caused to the property. And then the firefighters also, while controlling the fire, they have to access. So the smoke removal is important from that perspective also. And after the smoke fire has happened, smoke purging is also required. So for that purpose also, the smoke management systems are required. And then it's also the objective of smoke extraction is to maintain the tenable conditions on egress systems and refuge areas, so that the occupants, they can escape safely. Now, there are various methods of smoke management which can be classified broadly in two parts: active method and passive method. So whereas passive method, it takes care of, it uses the building construction material to limit the spread of smoke in a structure by maintaining the compartmentation, by creating the fire-rated walls, barriers, fire dampers, smoke vents, and shafts. So these are using the building systems. And then we have the active methods, which uses the mechanical equipment to control the spread of smoke in a structure. These further, they are also classified. They have the different forms like exhaust, dilution, airflow, pressurization systems, and all. So guys, subject is vast, but in this session, we'll be concentrating only on the last point D of the active methods, which is the pressurization system. So now what is the requirement of the pressurization? Now, International Building Code, it recognizes three specific means to provide area smoothly. One is the natural ventilation, where there can be certain openings left, as NBC 2016 has also said that you can provide 0.5 square meter opening in the staircases which are exposed to the outside. So it can be a natural ventilated, then you don't need the pressurization, or it can be mechanical ventilation of a stair. And third option is the staircase pressurization. But you see, there are architectural issues related to providing the external stair balconies, because everywhere it is not feasible. And then cost issues are related to the mechanical pressurization system, because it adds to the additional and operating costs. So the staircase pressurization system, that is the most widely selected option. So in this session, I'll discuss the smoke control system and the design considerations which are more associated with staircase pressurization systems. And likewise, lift lobbies and lift wells are also part of egress routes as a link with the stairwell pressurization system. So they'll also be covered in this session. Now, coming back to the pressurization, when we say that like pressurization systems, they're meant to protect zones away from the fire sources like the exhaust ventilation or dilution. Those are the other techniques. So these two figures depict that what will happen in a building in case of fire where the pressurization control is not provided. The smoke will travel to the other floors through the lift wells, through the staircases, through the building structure, and the whole building will be full of smoke. Whereas where a pressurization control system is provided, we maintain the proper gradients between the escape routes and the fire affected area. Say this is your stairwell and this is the lift lobby, which are both a part of the egress route. They are maintained at a positive pressure with respect to the fire corridor, which is the zone C. So this active method pressurization system, it is installed on stairwells, it is installed on elevator shafts or lift wells, it is installed on lift lobbies and the egress routes. What are the specific needs of staircase pressurization? It's basically to protect life, to reduce damage to property, to inhibit migration of smoke to stairwells in the areas of refuge and the similar egress area, to maintain the tenable environment in the refuge areas and in the egress routes, and to facilitate fire and restore operation after the fire has happened. You have to improve the visibility to purge out the smoke and for protecting the occupants. So it will ease out the work of the firefighting crew. So this is the typical staircase pressurization shaft diagram. So in case of fire, staircases will be the normal route. The people will be escaping from their respective floors to the main outside door. And this is a figure which shows the staircase pressurization fan which is normally installed on the top of the building, the terraces. This is a blow-up diagram. Then the other one is the lift well pressurization, because lift well is a vertical connection. In case of fire, it is very critical because otherwise, if it is not pressurized, smoke will distribute through the stairs and the lift shafts and in the corridors of the upper floors, and the occupants will be trapped by the smoke on their way into outside building. Now, what is the difference between lift lobby and lift well pressurization? So here we see these are the lift lobbies on the different floors. So the idea of lift lobby pressurization is to prevent smoke from migrating from one floor to another floor through the lift shaft. And this is particularly maintained at a static pressure of 25 to 30 mm. And the NBC says that if lift lobby is not enclosed in certain buildings, then lift well needs to be pressurized. Otherwise, the latest code NBC 2016, it has not mandated the lift well pressurization. We can do away with this if the lift lobbies are enclosed. And lift well pressurization, it is an alternative to enclosed lift lobbies. And if it is done, it is maintained at 50 mm static pressure. It prevents smoke flow through lift shafts. But normally, for additional safety in our designs, we provide both the lift well and lift lobby, the wells being kept at a level of 50 mm static pressure. The lobbies are maintained at around 25 to 30 mm static pressure. So how this pressurization is created? There are two sides. One is the high pressure side and one is the low pressure side. High pressure side is maintained in the refuge areas or the exit routes like the stairwells and the lobbies. And low pressure side is the affected accommodation side or the fire zone corridor. Now, what are the principles, how it is implemented? This system uses mechanical fans to produce the positive pressure on the stairwells or on the lift lobbies and on the lift wells. And for example, if we say A, B, C, the pressure gradient which will be maintained will be A greater than B greater than C. And the idea being when these doors are open, the air should flow from A to B to C and not vice versa. This will control the flow of smoke and migration of smoke to the exit routes. So in the door close scenario, what happens when both these doors are closed? Excessive pressure in A and B, it will prevent the smoke migration from zone C to these places. But at the same time, the caution is that the pressure maintained should not be so high that the door opening is a problem during the egress. So and the second situation is when these doors are opened. Suppose this door between the affected fire zone, that is a corridor or accommodation side, and the lift lobby, it is opened. Then the pressure tends to equalize between the two zones. So in the design, the provision is kept for that condition of opening of door, that when this door opens, there should be sufficient air quantity provided that air rushes across this door at a specified egress velocity of around 1 meter per second, which is stipulated by the standards, and or around 200 fpm. and then it will prevent the smoke to migrate from C to B even when this door is open. Now there are certain stipulations of NBC 2016 regarding the ventilation or pressurization requirements of the staircases with respect to the location of the staircase in the building and also based on the building heights. So it says that for the internal staircases with external wall, that is a external exposed wall, if the building height is less than 15 meter, then the staircase can be naturally ventilated. And this does not apply for the residential buildings. The louvered area also specified by them is 0.5 square meter. Now for the buildings with height between 15 meter to 30 meter, the stipulations are either the staircase should be naturally ventilated or it can also be pressurized. For buildings more than 30 meter, it has to be cross ventilated or pressurized. Cross ventilation means the staircase needs to have louvers into opposite side walls or two adjacent walls, or it should be ventilated across the corridor. Now the second option is the internal staircase, which is not adjacent to an external wall. For such staircases, for the building height less than 15 meter, it's required to be pressurized, and even for the higher height buildings between 15 meter to 30 meter or more than 30 meter, the regulations necessitate the requirement of pressurization of buildings. Only for the buildings, residential buildings are exempted from the pressurization requirements. Now, what about the pressurization levels? Again, as per the codes, it says that the pressurization level in the staircase, it should be not less than 50 Pascal between the exit staircase and the accommodation. When all the doors are closed, the pressure should be 50 Pascal. And if there is a smoke stop lobby, there is an adjacent lobby or a lift lobby, then the pressure at the exit staircase should be higher than the lift lobby. So as we saw in the previous slides, if it is 50 Pascal here it is around 25 to 30 Pascal. And at the same time, the force required to open any door against the combined resistance of pressurizing air and automatic door closing mechanism shall not exceed 110 Newton at door handle. So this is also a typical requirement that there should not be any problem due to excessive pressurization in opening of the doors. Then third point is the egress velocity. So when this is a situation when the doors are open, the pressurization system should provide adequate airflow, which can enable the adequate air velocity of 1 meter per second from the open door. And flow velocity shall be attained when a combination of two doors from any two successive stories and main discharge door are open. So NBC says that like when we are designing the pressurization system, it should consider two doors and one main discharge door. But like in certain standards, they even accept one door considered as the open door, and the main discharge door in any case has to be open for the escape of the occupants. And the egress velocity minimum should not be less than 1 meter per second. Then, as I said, there are leakages through the structural elements in the building. So the pressurization air that should be sufficient to make up for the loss of air through the leakages into the unpressurized areas. Now, where are these leakages happening? These can be around the perimeter. If we consider a room, there are doors, there are windows. So there are leakages across doors and windows, and also across the building structure, the walls, the ceilings, the floors, and then if there are special extraction systems, those also have to be taken into account. Then in the design, we have to decide the number and distribution of injection points. If it's a multi-storied building, at which all points we need to inject the pressurization air. At the same time, the pressurization system, since it is to operate during the emergency call, it has to be fed through a reliable operation through the emergency supply. Then it is a requirement that the supplier has to be drawn directly from the outdoor space. Sometimes people tend to consider the fresh air coming from the basements, but that is not done. The air, as per the regulations, the air has to be drawn directly from the ambient. And the pressure air intake shall not be less than 5 meters from any exhaust discharge opening. The pressurization system shall be automatically activated by the fire alarm system. Now, as per NFPA 92A, it also stipulates the pressures depending on the ceiling height in the sprinklered or non-sprinklered building. So it says that for a sprinklered building, if the building is provided with the sprinklers, for any ceiling height, the design pressure difference should be minimum 12.5 Pascal. With a non-sprinklered building, for a ceiling height of 9 feet, you need to maintain and design for 25 Pascal static pressure. For a non-sprinklered building of slightly higher height, that is 15 feet, the design pressure difference should be 35 Pascal. And for a high-rise, high-floor building, which is not sprinklered, you still need to maintain the higher pressure of 45 Pascal. So minimum pressure value in a sprinklered building is 12.5 Pascal. Maximum pressure value which is allowed is 112 Pascal, because beyond that, as we said, that the door openings can be problem. And generally the pressure is around 88 Pascal, and door opening force is specified to be 30 pounds. Now, what are the system components of the staircase pressurization system? It is one, we have to decide the supplier quantity, the air which is to be injected into the area which is to be protected. Then we have to also provide for the relief air mechanism to avoid or to release overpressure when the doors are closed. System components also include the supply fans, the distribution system like ducting, grills, vents, and then for the relief mechanism, we need to provide automatic air release vents or dampers. Then we have the automatic control systems which will actuate the pressurization system. These include fire alarms, smoke detectors, and safety switches. Then there is also classification of staircase pressurization systems. They can be classified as compensated or non-compensated pressurization system, single or multiple injection system, top or bottom injection pressurization system. So now what is compensated system is the type of system which can adjust to any number of combination of door openings. So as we are assuming one or two door openings, but in compensated system, any number of doors, if they are open in the building, the system should be able to pour in that extra air to maintain the pressure differentials. And how it works by changing the airflow, modulating the airflow, and at the same time, if the excessive pressure is built up, it will relieve that from the stairwell. But the thing is that the system is more complex, costly. It has more components like sensors, relief dampers, VFDs, and certain control sequences have to be worked out for how these will be operated optimally. The non-compensated systems are the normal systems which are used in the buildings. So they comprise of the single speed fan, which are constant volume fans. And here we decide that we are designing for how many number of doors are open. So level of pressurization depends on the number of doors open, because if the door opens, the pressure in the stairwell will drop. Whereas if the door closes, pressure in the staircase will rise. So it is this type of a system is more applicable for the situations where the normally the access doors are closed, and whenever they are used, they are open for few seconds only. So like we can consider the normal office high-rise buildings also the same situation happens. Now, depending on the location of the pressurization fan and also number of the injection points, how the pressurized air is being introduced in the stairwell, it can be a single injection system where the in the single pressurization system, we provide the pressurization air at one location as we are showing in this figure. So the fan is installed at the terrace and air is injected at one point. But the drawbacks of this method is that system can fail if the access door opens near the injection point. Say like if we have the door opened at the upper floor only, the air is going to leak out into that particular floor and the balance areas will remain unpressurized, and then loss of pressurization will happen immediately at the access doors farther from the injection point. The lower floors will not receive the pressurization, and here the most common injection point is top of the building. The fan, as we saw, it is installed on the terrace. Then we have the multiple injection pressurization, which supplies air from more than one location. As we are seeing, we need to have a duct, vertical duct, and the air is injected at different levels. So it employs either multiple fans, either you can have a separate fan for one or two or three floors, or it can be a single fan which is connected through a ducted arrangement to the multiple outlets. And normally acceptable points are that like we need to inject the pressurization air after every three floors, but the maximum is five floors. But in the normal designs, we recommend that when we are laying the duct, let us provide the pressurization at every landing. Now, based on the location of the pressurization fan, again the pressurization system is classified as the top injection system or the bottom injection system. Now, what is the difference between the top and what are the merits and demerits of the top injection and bottom injection system? In the top injection system, fan is at top of the stairs and it occupies minimum footprint. It will not block the premium space. But the drawback is that the highest pressure will be there at the top of the stair and the lower pressure is there at the bottom. And security is a concern because normally the fans will be in open. In the bottom injection, fan is at the bottom of the stair and it takes up the valuable ground space. And at the lower pressure, uh, as we go up on the floor, the pressurization level will be reducing at the upper floors. Higher pressure will be at the bottom. Security is relatively less issue. Now, what are how do we go about designing a staircase pressurization system? We need to consider the following points, like supplier fan options. Where do we have to locate the fan? How we have to select the fan drive? How the pressurization fan will be activated? What will be the distribution arrangement of the pressurization air? What will be the specification of the ductwork? How we design for pressure relief venting? What are going to be the design calculations? What is the design criteria? How the system works? And then the documentation has to be there, handy with the building all the time, because the regular fire drills and inspections are an important part in the building. So one needs to maintain the basis of design and documentation. Now coming to the first point, we have two options of supplier fans. One is the centrifugal fan or second is the axial fan. In centrifugal, as we know, the airflow is in radial direction of the impeller and it can provide adequate capacity airflow and generate adequate static pressure too. In the axial fans, it generates airflow parallel to the impeller, and this fan can also provide adequate capacity and airflow and at the desired static pressures. Now, what is then preferred, whether a centrifugal fan or an axial fan? Preferred is axial fan because of the characteristic curves of the axial fans. Axial fans, they have relatively flat pressure curves. So with the variable varying flows also, like when the doors open or close, they will respond quickly without changing the airflow capacity and without major pressure fluctuations. Also, they are easy to install, occupy less space, and are usually less costly. But the drawbacks are that they are affected by the wind pressure and they may require wind shields at the air intake, particularly when they are wall mounted. But like normally these fans for the staircases are mounted on roof. So there, they are generally mounted with their axis of the impeller is parallel to the direction of the wind. So it is the problem of the wind pressure is less severe. Then location of fans, whether top or ground, then in that case, the top location is preferred because ground level will have the single main entry door or exit door, which will be open during the fire. So if the pressurization fan location is near to that, it may, um, there it will be affected. It can be disturbed by the man movement because of the fire personnel entry or for the refuge escape operation, which will cause short circuiting. And if the fire zone fire also happens to be nearby, then it can also, we need to avoid the smoke toxic gases entering into the air. So the it is preferable to locate the fan on the terrace on the top, and that too, as per the regulations, they suggest two fans with the air intakes even on the terrace and which are facing from the opposite directions, so that if there is a fire at the top also, so the pressurization air being sucked by that fan should not bring in the smoke, and it will be sensed by a smoke detector which will be installed in the system. So as per the norms, each air intake shall be protected through a smoke control damper, so that if one damper closes due to smoke contamination, other air intake supplies air without interruption. And each inlet shall be suitable for providing the full. It should be designed for the total pressurization quantity and not 50-50. Then the air inlet shall also not be less than 5 meters away from any exhaust discharge opening. And air intake shall be independent. It should not be influenced with the wind speed and direction. How we select the fan drives, the smoke control fans, they are required to operate at below their rated horsepower. And they should be selected with the service factor of 1.15. They should be designed to run in the stable portion of the fan curve so that the air quantity is not modulated much due to the pressure differentials when the doors open. They should be suitable for operation at elevated temperatures. So that is why it has been specified that the fans should be suitable for 250 degrees centigrade to be withstand. They should be able to withstand this temperature for more than 2 hours. And how the pressurization fans will be actuated? The actuation can be manual or it can be automatic through the fire detection system. And additionally, certain state codes, they also mandate that there should be a manual switch at the entrance gate so that the people don't have to go in to switch on the system. How the distribution arrangement, how the ducting arrangement will be designed. It can be a single fan serving a vertical duct with providing horizontal branches to each floor, or it can be multiple fans serving multiple floors. Now, how the location of the vertical duct can be placed? It can be placed in a dead area or a non-critical area in various types of configurations depending on the building and the core layout. Say for this picture is showing this pressurization duct, which is a shaft supplying to the lift lobby and to the staircase, and the shaft is designed in the toilet. In this case, if we are not getting the face of the staircase or the lobby, then you can have it inside, but then the connection has to be through a fire rated duct. This has to be a fire rated duct supplying pressurization air to the lift lobby. And then in certain cases, and a preferable option is to have a backside shaft in the stairwell itself. So we can have a masonry shaft in which the pressurization ducts can be laid for the staircase as well as for the lift lobby. So this is a blow up, which is showing in the 3 configurations. Then coming to the ductwork, now the specifications of the ductwork for the pressurization, since the supplier ductwork, the pressurization system ductwork can have the same specifications as the normal comfort HVAC, and you can also pump in air through a masonry shaft, but it is not a very good option. One, it also causes leakage because of the permeable structure. It causes excessive pressure drop, and then if it is a high-rise building, you cannot give the cross-sectional change which will determine the proper velocity at the lower levels. So we do not recommend the use of masonry shaft. Then how do we design the pressure relief venting? So that is to prevent the build-up of excessive pressure in the stair when the doors are opened and closed. So when door is opened, the pressure in the stair reduces and the relief vent closes. When door closes, the vent will open and to release the excessive pressure which is developed in the stair, so that the door opening forces are reduced. Now, what are the different mechanisms of relief methods? One is the automatic opening door. When the excessive pressure builds up in the corridor, you can have electrical interlocking connecting with the differential pressure sensor in the staircase. So it will cause the automatic opening of the door. But the limitation or drawback of this method is the security. You can provide vents at each floor to relieve the excessive pressure. You can have barometric dampers. Then you can have the motorized dampers, which will take the signal from differential pressure sensor between the stairwell and the accommodation, and accordingly it will release some air into the stairwell. We can have exhaust fans to relieve the excessive pressure. Then we can also reduce the pressurization here by bypassing some amount of air across the fan itself. Other option is we can have a variable frequency drive for the fan. The fan can be provided with the VFD, again, which can modulate the air quantity based on the signal from differential pressure sensor. Now coming to the design calculations in detail, we need to know now what is the minimum pressure difference which is allowed between the staircase and the adjacent accommodation. Delta P minimum is the minimum pressure difference. As per NFPA 92A, table 5.2.1.1, it specifies a minimum pressure of 0.18 inch or 45 Pascal between staircase and the adjacent accommodation. And the delta P maximum, the maximum pressure difference between the staircase and adjacent accommodation, is mentioned to be 0.37 inch water gauge or 90 Pascal. So when doors are open, IBC calls for 3 doors open, air velocity of not greater than 200 fpm through the doors. So around 1 meter per second or 200 fpm is the egress velocity across the door is specified. And the maximum force required to open any door, a door handle, should not exceed 30 pounds. So how do we go about designing the pressurization air quantity? Seeing the layout of the building, we need to identify all the airflow paths from where the leakages are bound to happen. We calculate the leakage rate at each of these elements. Then we identify all the airflow paths with the doors closed, when the doors are closed, and calculate the leakage rate for the gaps around the doors or windows. We also give a contingency and increase the air quantity by 50% for the unknown leakages. Then we identify all the open doors and see what is the air quantity required to be added in the pressurization calculation when the door when the door is open and the air has to rush from the door at a velocity of around 200 fpm, and then maybe 15% can be added to that also for to take care of the losses to the ducts. Calculate the total airflow with all the balance doors closed and only 3 doors open, one main ground floor escape door and 2 doors on any successive stories of the building, and determine the fan capacity. Check that the door opening forces are below 30 pounds. Then calculate size of the pressure relief damper. This is a formula calculate the air leakage. So how we calculate Q is equal to 2610A delta P raised to power 1 by 2, where Q is airflow leakage in CFM, 2610 is a constant, A is total leakage area that is calculated in square feet, and delta P is differential pressure in inches of water. In SI units, the formula is Q is equal to 840A delta P raised to power 1 by 2. Here you will get the airflow leakage in liter per second and the air leakage area in square meter, and delta P is in pascals. So total airflow requirements can be computed as Q total is equal to Q1 plus Q2 plus Q3, where Q1 is the leakage through gaps in the building construction. As I said, there will be leakages through the walls, through the ceiling, through the floor, because the structure is permeable. Q2 is the leakage around the doors or windows which are there in that particular area. And Q3 is the air quantity which is required to take consideration of the open doors. This is a table available in NFPA 92, which gives based on the tightness of the building, how much will be the leakage area depending on the construction elements. Say, if we have stairwells, stairwell walls, for average tightness, the leakage area is 0.11 into 10 raised to power minus 3 square meter. If it is elevator shaft walls, if it's an average construction, the leakage area is 0.84 into 10 raised to power minus 3 square meter. Similarly, for the floors, which includes construction cracks and gaps around the penetrations through which the leakages happen. For average construction, average tightness of the floor, the leakage area is 0.52 into 10 raised to power minus 4 square meter. The same figures apply for the ceilings as well. And then if we come to leakage areas around the doors or windows, so where are these leakages happening from? These are happening from the perimeter of the doors or windows. That means 2 times the height and 2 times the width, and the crack length. What is the gap? Which is normally assumed to 5 or 6 mm. And it also depends on the single leaf door or a double leaf door. A single leaf door of regular size 3 feet by 7 feet will not have the middle central gap. The perimeter will be the 2 heights and 2 widths, and leakage area, if for a gap of 6 mm, leakage area will be calculated as the total area into this is 0.12 square feet. Crack length into gap is 0.12 square feet. Now for a double leaf door, here your crack length is the perimeter plus the central height. So that becomes, in a case of a 6 feet by 7 feet, so you have 6 plus 6, 12, plus 7, 19, plus 7, 26, plus the central 7 makes it 33 feet, and the gap of 6 mm, and the multiplication of this 33 feet by this, the total leakage area for the double leaf door computes to 0.2 square feet, sorry. Now leakage through the open doors. How do we compute the leakage through the open doors? Q is equal to V maximum into A door. Q is the flow rate through one open door in CFM. V is the maximum air velocity, which is stipulated as per IBC as 200 FPM. A is the effective opening of the door in square feet. Now, if in a case, if the doors are in parallel, then the effective leakage area is, total effective area will be A1 plus A2 plus A3 plus A4. And for the doors which are in series, the effective leakage area is given by 1 by A1 plus 1 by A2 plus 1 by A3 plus 1 by A4 whole raised to power 1 by 2. This is how we can then calculate the fan capacity, find out the total leakages and total volume flow rate we have evaluated. Then that is the total supply to the pressurized area, add 10% safety to it, find out the total pressure of the distribution system and decide on the fan static pressure to be maintained. The supply outlets, the grills at each of the landing is designed at a velocity of 500 to 600 FPM. And then the venting requirement to provide the relief in case of overpressure. It is calculated by sizing the relief vent damper. For this, we calculate the air leakage when all the doors are open minus air leakage when all the doors are closed. The difference of the two divided by 2000 FPM gives the square feet of the relief damper required to be designed. And it should be adjusted when we are providing the relief. Minimum 25 Pascal pressure should be maintained in the stair well, in the stair shaft. So now coming to case studies and the details of the design calculations, we will take up one calculation each of staircase pressurization, lift lobby pressurization, and lift well pressurization. So this is a case of a building which is extending from ground floor to 25 floors. That means total 26 floors. This is your lift lobby and this is the stairwell. Both have a single leaf door of 1200 wide by 2100 high. Coming to the staircase pressurization calculation, now as we discussed earlier, the pressure difference required to be maintained in stairwell is 50 Pascal. Egress velocity required to be maintained is 1 meter per second. Total number of floors which get calculated, if the building is from ground floor to 25th floor, there are total 26 floors. Now type of single leaf doors, door type is single leaf and the door size is mentioned to be 1200 wide by 2100 high. So how we calculate the leakage length is the perimeter of the door 2 into W plus H or 6600 millimeter. Air leakage gap is assumed to be door crack to be 5 mm. So leakage area can be calculated as 0.033 square meter, like the multiple of this. Now, as per ASHRAE 2021 and as the formula we discussed earlier, the flow rate, the leakage flow rate across the closed door, it will work out to 0.839 into A into under root of P into 2118.9, where Q is the quantity of air in the CFM, A is the leakage area in square meter, and P is the pressure differential in Pascal. So leakage air through one closed door from this formula And from A, we have calculated here. P is the Pascal, 50 Pascal. Into this gives a value of 415 CFM. That is the leakage air through one closed door. So here in this case, we are assuming that out of 26 floors and 26 doors, 2 are open and 24 are closed. So leakage air through 24 closed doors will be 415 into 24, that is 9956 CFM. Then we have to add in the leakage through the open door. Door size again is 1200 by 2100. Leakage area becomes 2.52 square meter, and the formula is Q is equal to A into E into 2118.9, where Q is the air quantity in CFM for the open door, A is the leakage area, E is the egress velocity in meter per second, that is 1. Now leakage area through one door from this works out to, this is 2.52, that is the area, into 1 into 2118.9 gives 5340 CFM. Likewise, we are considering here 2 doors to be open. So 5340 into 2 is 10679. So now how we can calculate the total air capacity of the fan required is the total leakage to the closed doors and total leakage to the open doors. So 9956 plus 10679, 20,650 CFM is a minimum requirement. You can add a factor of safety also to it to be on the safe side. Then lift lobby pressurization calculation. Now here it is a calculation is almost similar to the staircase pressurization. Only thing is that the here pressure difference which is to be maintained in the lift lobby is between 25 to 30, whereas in staircase it was 50 Pascal. So pressure differences we are taking is 30 Pascal. Egress velocity through the open door to be maintained is 1. Case is same, ground floor to 25 floors, we have 26 floors. Same door size we are assuming 1200 by 2100. Leakage length across the closed door is 2 into W plus H, and the leakage area computed to 0.033. So leakage through one closed door in this case works out to 321, which is slightly less than that in case of staircase pressurization, only because of the fact that here we are maintaining lower pressure differential. So leakage air through 24 closed doors works out to 7704 CFM, and then we have to consider the total air quantity for the 2 open doors. So leakage through open door of size 1200 by 2100, it is again based on the same as we worked out in the previous case. It works out to 5340 CFM, and because the formula is same, 2.52 into 1 into 2118.9, which works out to 5340 for leakage around one open door, and likewise for leakage air around through 2 open doors we have 10679. So the total leakage is 7704 plus 10679, which works out to 18383. So you can select a fan of 18,500 CFM. This is the third case which talks about the lift well pressurization. So in lift well, as we discussed, the pressure required to be maintained is 50 Pascal. We have total number of floors as ground floor to 25 floors, that is 26 floors. Here the width of the door taken is 1000 by 2100 high, but it's a double leaf door. So the leakage length is the perimeter plus 1 vertical height. That works out to 8300 millimeter. Air leakage gap is assumed to 5 mm. The leakage area is 0.0415 square meter. So the total leakage across the closed door is again given by the formula Q is equal to 0.839 into A into root P into 2118.9, where Q is quantity of air in CFM, 0.839 is the factor, A is the leakage area in square meter, and P is the pressure differential to be maintained. So putting all the respective values in the formula, we get leakage air through one closed door as 522 CFM, and likewise, we have 26 floors, but in case of lift well, only one door will be considered as open door. So leakage air through 25 closed doors will be 522 into 25 is 13,050 CFM. Now leakage through the open door of size 1000 by 2100 is again calculated by the formula A into E into 2118.9. So putting the respective values in this formula, we get the leakage to the open door as 4447 CFM. The fan capacity required for the lift well is the sum of 13,050 plus 4447, that is 17497, or it can be rounded to say 17,500 CFM. Now, that was about the three calculations where we need to provide the pressurization systems. Now, this is again a typical example of an office stairwell where we'll be considering all the elements, the leakage through the building structure and through the openings. And here, I can just read out the requirement. It is estimate the pressurization requirement for an office stairwell that runs 5-floor level. So there are 5 floors in the building. Each floor has a height of 17 feet and it is 28 feet wide. That means this dimension is 28 feet. And this is 28 feet by 48 feet long. 48 feet long. It has 2 single leaf doors of 3 feet by 7 feet and a double egress door of 6 feet by 7 feet. We have to assume 3 doors are open and the maximum differential to be maintained between the stairwell and the office is 0.37 inch of water. So these are the requirements and we need to design the pressurization system for the same. So this is a table I showed earlier where based on the tightness of the structure, it gives the leakage rate for an average construction for the stairwell walls, for the floor or ceiling walls. So these will be made use of in this assignment. So we now see that what is the leakage across the walls? Height we said is 17 feet. Length and width of the area are 28 feet by 48 feet. 28 by 48 is the length and width. The perimeter is 2 into 28 plus 48 is equal to 152 feet. Area is 152 into the height 17, that is 2584 square feet. Now, average leakage ratio, as we saw in this table, for average construction is 0.11 into 10 raised to power minus 3. So we use the same value 0.11 into 10 raised to power minus 3. The total leakage area into the leakage CFM, leakage area for the space, it becomes 0.28 square feet. On the floor, the area is 48 into 28. The floor area through which the leakage will happen is 28 into 48 is equal to 1344 square feet. And from the same table, for an average construction floor, the leakage area will be 0.52 into 10 raised to power minus 4. So applying this leakage ratio of 0.52 into 10 raised to power minus 4 into the floor area, the total leakage area becomes 0.14 square feet. Likewise, for the leakage from the ceiling, we take the total area as 28 into 48 into the same air leakage ratio of 0.52 into 10 raised to power minus 4. the leakage area is same as the floor, that is 0.14 square feet. Now we have basically three two single leaf doors, A2 and A3. So A2 and A3, it is the height of the door is 7 feet and one door is 3 feet. So the total, we can say combined width is 6 feet. The gap length is the perimeter, 7 plus 7 plus 3 plus 3. And the door crank is assumed to be 6 mm. That means the total leakage area is 0.12 per door. And for two doors, it works out to 0.24 square feet. And for the single leaf door, which is 7 feet by 6 feet wide, the gap length is the perimeter, that is 7 plus 7, 7 plus 7 plus 6 plus 6 plus the vertical height 7 feet, which is additional. So it is 33 feet. So door crackage here becomes 0.006 and the total leakage area is 0.2 square feet. So airflow through the gaps in building construction, it we term as Q1, airflow around the door gaps as Q2, and the total airflow will be given by Q1 plus Q2 is given by the formula Kf into A into delta P raised to power 1 by 2, where Q is the leakage CFM and K is the coefficient 2610, A is the flow area and delta P is the pressure differential to be maintained, which is in this case given to be 0.37 inches of water. So volumetric flow rate, the total leakage through the for Q1 and Q2 for the building construction and the door gaps becomes 2610 into 1 into 0.37 raised to power 1 by 2, because the flow area is 1 square feet. So it works out to 1587 CFM per floor. So that is for the building structure. And number of floors of the stairwell are 5. So the total volumetric flow rate, the total leakage through the structural walls, ceiling and the floor works out to 1587 into 5, which is 7935 CFM. Now airflow through the open doors. So we are assuming 3 doors to be open. One is 5 into 7, the double leaf door. Other one is 3 by 7, 3 by 7. So the total open area is 35 plus 21 plus 21. So since the doors are in parallel, the effective leakage area is A1 plus A2 plus A3. 35 plus 21 plus 21, which works out to 77 square feet. So the total leakage across the open doors will be V maximum into AE, where V is 200 FPM is the egress velocity and A is the total leakage area, that is 77 square feet, that is 15,400 CFM is the leakage to the open doors. So total air for pressurization will work out to the leakage through the gaps in the building construction, leakage around the door gaps and leakage through the open doors. That is Q1 plus Q2 plus Q3. That is 7935 as we worked out in this condition, 7935 and 15,400 for the open doors, that is 23335, say 24,000 CFM. So this is the capacity of the fan or the pressurization air required. Now how we design the supply outlets. Now this air quantity is to be divided at 5 levels. That means approximately 4,800 CFM at each supply outlet. And we said that the grill is to be designed for 500 to 600 feet per minute. That means a cross-sectional area of 4,800 by 600 or 8 square feet grill will be required. Then we have the venting requirements, how much relief should be provided. That is the air quantity with the 3 doors open. And then considering all the doors closed. So this is the differential 15,400 minus 7,935 is the relief air requirement is 7,465, and pressure relief damper is to be designed for a velocity of 2000 fpm. So that means we can design it for 7,465 divided by 2000 fpm. Around 3.7 square feet is the uh, cross section of the relief damper required. So that was all, guys. That completes the total calculation. Hope you are clear about it. Thank you so much.